Started. We're going to talk about atoms again today, talking about how quantum physics now plays into atoms. And so we saw the Bohr model that said we have a quantized angular momentum. That's what Niels Bohr set as his quantum hypothesis, or I can't remember quantum hypothesis versus quantum condition. But he said that the angular momentum can only have values of n times h bar. And based on that and his requirement of circular orbits with stationary energy states, we're able to then, just using the quantum physics, using standard physics after that, come up with a model that gives us energies for electrons and matches the spectrum of energies that we see when we bring out a lamp and look at the different colors of light. So it's a great step forward, but it's not perfect because it has some problems that it can't do. For instance, it can't explain why some emission lines are stronger than others. It just doesn't explain the variation in strength of emission lines. And it can't explain what we call fine structure observed in the emission lines. Little variations. The lines sometimes don't have just a single line, they'll vary. Or if you put them in magnetic fields, you'll have them change and split. It couldn't explain those. So the quantum model was built up based on the quantum physics ideas we talked about last class period to overcome these. Now, the quantum model has two different ways it was derived. I mentioned this 2 weeks ago in the Physics 252 class. One method was to say, now, where's the electron? I don't know where the electron is. Scientists determined that there was no way of determining where the electron was in an atom. And so Werner Heisenberg said, okay, forget about that. Let's just worry about what the properties are of the electron. And so we know the electron is going to have things like a magnetic moment. If you put it in a magnetic field, it shows that it has a magnetic property. And they decided, well, what can make an electron have a magnetic moment? It must simply be a charged particle spinning. And so they called that magnetic moment, they called the spin. Now we understand things differently today. No one believes that electrons spin. So like in your chemistry class, probably all along when you talked about the spin of an electron, you thought it was spinning. It's anachronistic. They thought that it was spinning, but it turned out they were wrong. It's not. And so he just classified these and came up with a way of organizing the behaviors. And then there's Erwin Schrödinger, who came up with a wave equation to find a wave function to describe these. Both of them come up with the same results, and they only calculate probabilities. Things like we can calculate the probability of where we're going to find the electron, not, this is where the electron is, or this is the path. No one knows what path an electron takes. So our model of an atom, a hydrogen atom, looks something like this. We have in the center of the nucleus, and then we have that lime greenish color is where the negative charge is. Now, a neutral hydrogen atom has just one electron. So that's one electron, and that color is spread out, showing us where we're going to have more negative charge and less negative charge. Or, putting it more realistically, if we were to measure where's the electron, where it's darker, we're more likely to find the electron. Where it's lighter, we're less likely to find the electron. The electron could exist very far away. It's just really, really unlikely. That's what quantum physics tells us about the atom. And it's not very comfortable because we like to think, okay, so here's the atom, here's the nucleus, the electron's on this circle. It's just going around, 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 around. That's what we learned in high school, right? But that's not right. We know it's not right. It's just a model that helps us to visualize better. So what do we get? We calculate a wave function. So here's the wave function for an electron in what we call the 1s, which I'll get to what that means. Now this is psi. That is, how do we go from psi to probability? We have to square it. First step. We have to square this. So if we square this, what's going to look like? Psi mod squared, what would it look like?
Just the same thing, but higher up.
Yeah, it's just going to be, okay, bad curve there. It's going to be something like that. If that was the end answer, then that would say, where's the electron most likely to be found? At a radius of 0. It'd say the electron is most likely to be found at a radius of 0, which means in the nucleus. But that's not all of it. We don't just plot psi squared. We have to do psi squared. Now, it was dx. You know, what's the probability of being a small range dx is what we did before because we were working in 1 dimension. Now we're working in 3 dimensions. If we're using radius, then I'm going to have in a d area, a little bit of area in a spherical shell. And so that little bit of area is going to be, actually volume, 3 dimensions. It's going to be area times dr to give us a volume. And so that's going to be d volume, where d volume is the area of a sphere, 4 pi r squared times dr. So I have to take 4 pi r squared dr and multiply it by my psi mod squared to get the actual probability of finding the electron in a given radius. So here's a graph that shows what those two functions are graphed separately. So psi mod squared is the first one, 4 pi r squared is the second one. You multiply those two together, and you get this. So this is the probability of r. I should put dr there. This came from a textbook. It's not my bad. The probability of being at a radius r dr, and you find this here. Notice the units. A0 is equal to the Bohr radius. And so the units for radius were in the radius divided by the Bohr radius. And what's the most probable position, the most probable distance for an electron to be from the nucleus? According to this graph, it's 1 Bohr radius. So the Bohr radius, the calculated radius for where the electron does a circle in the Bohr model, turns out to be the most likely distance from the nucleus for an electron in a hydrogen atom. So that Bohr radius we use all the time still today because it's exactly a correct calculation in the quantum model. But this says that there is a finite possibility of the electron being here. And there's a finite possibility of it being out there. And I'm going to have to measure to determine. There's no way beforehand to say, oh yeah, it could be, but it's not. You have to measure before you can say if it is or is not out there. Once again, that comes with the probabilistic nature of quantum mechanics. It's not deterministic. It doesn't say it's there. It simply says, well, it's got a certain likelihood of being here, a certain likelihood of being there. Now, our first of 2 clicker questions. What calculation gives the probability of an electron being between r and r plus dr from the nucleus of an atom? Between Caitlin, Jerry, and, well, Caitlin McCuther, Jerry, and Brady. Just so you know who's potentially coming up. All right, everyone has answered, and so we had a plurality that said F. There is no majority. This one here is going to answer. Jerry.
This might be kind of, and it also gives us the radius of this atom, since we're looking for the radius nucleus, what is going to be, so we'll find this one nucleus radius.
So it'd be F? Okay, now, why is there the 4 pi r squared dr part?
Because we're looking for the radius of where the atom is going to be within distance from the nucleus. And the 4 pi r
Okay, so because we're looking at the probability of finding it between here and here, the probability of finding it exactly at R is going to be 0, no matter what R is. We have to find the probability of being in some region, which if it's three-dimensional means some volume. And so that's the little piece of volume, which you said. So I'll give you 5. Okay, so all of these are things that are somewhat relevant, right? Psi is telling us about probability, but we have to take the square of it to actually get the probability, but then we have to also multiply by this piece dV. So this one had the dV but didn't have the square. These had the square. This had a dr, but because it's three-dimensional, we needed a dV. Okay, quantum numbers. Going through the quantum physics part in my class yesterday, and I told them I was disappointed that not one of you wanted to come and learn about the particle in the box. One thing that we did was we took the time-dependent Schrodinger equation, and through mathematical manipulation, we were able to separate the time portion from the position portion. And so then we had two different values that were equal to the same, or two different equations equal to the same thing. And that was the energy. Well, that gives us one quantum number. That quantum number we call n, the principal quantum number. The principal quantum number primarily tells us the energy. It doesn't exclusively tell us the energy. It tells us more than the energy, and it doesn't by itself tell us the energy. But that's what it primarily tells us. Now, before, with Bohr only had one quantum number. And what did that quantum number, according to Bohr, tell you? The what? According to Bohr, it told you the angular momentum. Remember, I wrote down the first slide. He said the angular momentum has to be an integer multiple of h bar. But then it turned out that with his requirement of circular orbits with steady state energies, it also told us the radius, it also told us the speed, told us the kinetic energy, it told us everything. Well, with the quantum model, not so simple. The principal quantum number still n, the same number that Bohr used, but it primarily tells us the energy. And then we take the equation and we go through and we have three variables: radius, angle in one direction and angle in the other direction, because we use spherical coordinates. And we separate it, so we separate the radius from the angular portion. And that gives us a second quantum number. And then we take the radial portion and we separate it into the two different angles, and that gives us another quantum number. So we have three quantum numbers that come from the calculus involved with the quantum mechanics. And then there's a fourth quantum number that we'll get to. So there's four total quantum numbers that we have to use to describe the state of an atom. Here's another thing that, honestly, only within the last few years have I really, really embraced. I always thought of these quantum numbers as describing an electron. So this electron has n equals this, L equals this, M equals this, you know. It turns out that you can't do that because you can't differentiate one electron from another electron in an atom. And furthermore, potential energy is not held by the electron, it's between the electron and the nucleus. So these quantum numbers are really describing the atom, not an electron in the atom. So what does that principal quantum number give us? Primarily this energy equation. Now, if you go on and take quantum mechanics, you will learn that this is not the final equation because you have a bunch of other things that play into it. Things like the angular momentum and the magnetic moment of the electron cause slight variations in energy. The magnetic moment of the electron, the magnetic moment of the nucleus cause slight variations in the energy. The fact that we have not taken into account relativity causes slight variations in the energy. So we go through and we do these perturbation calculations and we calculate the energy levels more specifically, and we find that the energy levels split up. And so even if you're in the n equals 3 state, if you're n equals 3, L equals 1, M sub L equals, you're going to have slightly different variations in the energies, which explains why the filling of the periodic table doesn't have, you look up there, scandium through zinc. Scandium through zinc are filling electrons associated with the third row, but they're in the fourth row because when you go to the quantum level there, you're filling a d orbital. The energy is actually higher than the s orbital in 4. So a 3d is higher energy than a 4s. And so that comes from using these perturbation calculations to get a more correct energy equation. Angular momentum is the next quantum number that comes out after n. That angular momentum is calculated from a quantum number such that total angular momentum is L times L plus 1. This h bar is outside of the square root, just to make sure it's clear. So the unit of angular momentum is h bar. Bohr said the unit of angular momentum was h bar as well. But what did Bohr have where this has the brackets? He said angular momentum was equal to h bar times n. With Bohr's, it was simple. The same thing that told us about the energy tells us about the angular momentum. But with the quantum model, it turns out, and this all drops out from doing the math, believe it or not, that the angular momentum is not an integer multiple of h bar anymore. It's the square root of L times L plus 1, where L is a quantum number that can be any positive integer up to n minus 1. N, the principal quantum number, has to be an integer that's 1, 2, 3, 4, 5. So we had n, wasn't written here. N is just an integer, and the energy is E1 z squared over n squared. And you look at that and you say, over n squared, that means if n is 4, I have 1/16 of the energy. Is that correct? Yes, you are correct if you say that. But notice that E1 is a negative value. So if you take a negative value and divide it by 16, you've gone up in energy. So as n increases, your number is getting closer to 0, but the energy is going up. As n approaches infinity, your energy approaches 0. If the energy of the orbital is 0, then the electron will be free to leave. If the energy is negative, then it's going to require energy to take the electron off. You have to raise the energy to 0 to get it free. And so when you're working with energies in atoms, you always have negative energies because for the electron to be bound, it has to have, has to have a negative energy. So n gives these energies, and 1 is called the ground state because it's the lowest possible state. What would your energy be if n equals 0 was possible? It'd be approaching negative infinity, right? Undefined. So it's not allowed, it's not possible to have n equals 0. And actually, once again, the relationships between n, L, those all come out of the calculus involved with doing the calculations. So for n equals 1, what values can L have? Only 0. If n equals 2, what values can L have? 0 or 1, and so on. And that means that your angular momentum, if n equals 1, what's your angular momentum going to have to be? It's going to be, if you want to be really technical, square root of 0 times 1 times h bar, which is, of course, 0. I just want to explain how it comes out. And if n is equal to 2, if L is 0, it's going to be 0. If L is 1, then what's its value going to be? Square root of 2 h bar. Square root of 1 times 2, which is 2, times h bar. And if n is equal to 3, you can have 0 square root of 2 h bar, or if L is 2, then it's going to be what? 2 times 3, which is 6, so square root of 6 h bar. That's telling us the total angular momentum. For classical physics, what does that total angular momentum tell you? Tells you what? Okay, classical physics, it tells you angular momentum is I omega. And so if we could figure out what the moment of inertia is for that electron orbiting the nucleus, which we would generally say I should be equal to mass of the electron times the radius n squared. You know, if I use the Bohr radius, for instance, then I could calculate the I, and this would tell me about omega, the angular velocity as it goes around circles. That would be classical. This isn't classical. We don't know what path it's taking. We don't know what its radius is. So I can't come up with an I. This equation isn't going to apply for me because I don't know what the radius is. So this is just telling me the angular momentum, and I don't know what path it's doing to get that. I mean, it could be going, you know, I don't know. But it has some angular momentum. And you notice these numbers, square root 2, square root 6. Square root 2 is, what, 1.41? Square root 6 is 2 point something. As you go up each time, you know, you have 1 times 2. The square root of 1 times 2 is somewhere between 1 and 2. 2 times 3, the square root of 2 times 3 is somewhere between 2 and 3. So each one of these is going up to a number between L and L plus 1 for its total angular momentum. That's actually going to be an important factor. Then we have the direction, the orientation of the angular momentum. The previous calculation was just saying, what's the total angular momentum? But now we say, well, what about its direction? What direction is it? You know what? The direction doesn't matter unless you put it in a magnetic field. If it's not in a magnetic field, it doesn't matter. But if it's in a magnetic field because you have a charge for that electron, its angular momentum is going to combine with its charge to give it a magnetic moment, to behave like a magnet. And if you put it in a magnetic field, if the magnetic fields are aligned, you have lower energy. If they're anti-aligned, it's a higher energy. And so the energy levels will change depending on the orientation of the angular momentum with respect to the applied magnetic field. As a matter of convention, we always assign the z direction is equal to the magnetic field direction. So that's just how we define it. Now you can see why when I was doing relativity, I said z instead of x. Quantum physics, it's the z that we define. So we just say the angular momentum component that's parallel to the applied magnetic field is going to have some value that ranges between perfectly aligned and anti-aligned. So let us take the example of, let's say L is equal to 2. If L is equal to 2, then the total L we just learned is square root of 6 times h bar, which means 2h bar is less than L is less than 3h bar. Right? And I want to find the orientation. What direction is the angular momentum? According to this equation, the orientation is going to have an integer multiple of h bar. So if and let me actually make a circle. There's a circle. There's a line. I've never done this so neatly. What this circle represents is L equals square root of 6 h bar. So the total angular momentum has to go from the center of the circle to some point on the circle. And we have different orientations. But then we had the only values possible were integer multiples of h bar. So here's 0 h bar, 1 h bar, 2 h bar, 3 h bar, minus 1 h bar, minus 2 h bar, minus 3 h bar. Now you can see right away, because the total angular momentum has to be on the red circle, and it has to be at one of those integer multiples of h bar for the z orientation, that your angular momentum has to be this, or this, or this, or this, or that. Those are the only options. It can't go to plus or minus 3h bar because that's bigger than the total angular momentum. This gives us right here something really, really bizarre about quantum physics. If I have a magnet, let's say I have the Earth's magnetic field, that's a magnet, and I put a compass here, how does the compass align? So it's parallel to the magnetic field. Why do you suppose, we've talked about it, why does it align so it's parallel to the Earth's magnetic field? Because what? Okay, it's an equilibrium. It's the lowest possible energy state. Right? I can hold it to a higher energy state, but if I let go, it'll have kinetic energy. It slowly gets dissipated, ends up at its lowest potential energy state. If I take the electron orbiting a nucleus and I put it in a magnetic field, it's not possible to align in the lowest position of being parallel. That's not an option. And when you think about that, it starts getting confusing, at least to me, because nature always wants to go to the lowest potential energy state. Now we're saying, but that's not an option. So the closest it can get is having 2h bar as the amount parallel. And so I can take this and I can actually calculate an angle. Can you see that color? Yeah. So theta, and I should put theta m sub L. We call the orientation quantum numbers m sub L. M for magnetic. Magnetic because we don't see any effect unless we put it in a magnetic field. The subscript of L because it has to do with the reaction to a magnetic field due to its angular momentum. So that's why I have theta sub m sub L. If I just take that arrow and draw it separately so I'm not messing up my picture, I have two sides of the triangle. This side of the triangle here is 2h bar, right? Because that's the z component. And what's the other side that I know of the triangle? The hypotenuse, because I know that its total angular momentum is L equals square root 6 h bar. And so if I want to find this angle, and this would be theta sub 2 to be correct, right? Because that's what our m sub L was there. I'm going to have opposite side over hypotenuse is sine theta. Notice the h bars cancel, and I'm left with sine of theta 2 is equal to 2 over the square root of 6.
0.816.
That's the 2 over square root of 6. And so what does that give me for theta 2? How much?
0.96 radians.
Okay, 0.96 radians. I would usually put it in degrees here because I understand degrees better than I do radians, but that's okay. Don't worry about it. What we have now is a calculation of how far it is from perpendicular. I can take the complement of this to tell me how close they are to parallel. So we can see, number one, why the allowed quantum numbers are going from minus L to plus L, because you have to have your x component of the angular momentum is less than or equal to your total angular momentum. And you can now see that you only have certain possible orientations. Now this brings up something I'm going to mention right here. You guys have probably heard about nuclear magnetic resonance, right? Well, what you're doing there is you are, okay, it says nuclear, so you're not dealing with the electron. You're doing the same thing, but with the nucleus of an atom. You put the atom in a very strong magnetic field. The nucleus is made up of course, protons and neutrons, like electrons, have a magnetic moment. So we call it a spin. And so the total magnetic moment of the nucleus is the result of adding up the spins of all the protons and the neutrons in the nucleus. And just like what we did here, if you put it in a magnetic field, it's going to try to align with that magnetic field. But it can't align. This couldn't align, the spins can't align either. And so you end up with magnetic fields like this, your magnetic moment, your spin of the nucleus is like this, and when you put in a strong magnetic field, it makes it precess, it makes it rotate around the axis of the magnetic field. And if you put in energy, you can make its orientation change to the other allowed state. You can make it go from like this to like this. And so with the NMR, you put a strong magnetic field to get it so it's as aligned as it can get. And then you put in an RF, a radio frequency signal, and at the right frequency, it will flip. So it goes to a higher energy state because it absorbs the energy and flips. And so you're measuring where did it absorb the radiation, and that's telling you then about, and we have the Larmor frequency that you may or may not have done calculations on, that tells you about what frequency you need in terms of the magnetic moment and the strength of the magnetic field. And so that gives you information then about the spin states. So let's talk about the spin state. Electrons are what we call fermions. Interesting history. Doing the quantum physics calculations, Fermi and Dirac calculated what would happen with particles' wave functions if the magnetic moment is 1/2 integer. That is 1/2 h bar. And what they found is if the magnetic moment is 1/2 h bar, then you have certain fundamental properties. One of those you know very well, the Pauli exclusion principle. Everybody's familiar with that, right? What's the Pauli exclusion principle?
You can't have more than, or the one electron has to have a specific set of quantized numbers. You can't have multiple electrons with the same set.
Right. You cannot have any two electrons that have the same set of quantum numbers. Now, it comes from a more fundamental quantum theory thing that from the Fermi-Dirac calculations that show that the wave function that you make for fermions has to be anti-symmetric. I can't remember the symmetry, but yeah, I'm pretty sure it's anti-symmetric. And if you were to have two particles with the same wave function, it would turn out to give you 0 for the wave function. If two particles are in the same state, you have 0 for the wave function. If you have 0 for the wave function, that tells you the probability is 0. So the quantum physics says if you have two particles that are fermions that have 1/2 integer spins. So fermions are defined as particles with 1/2 h bar or 3/2 h bar, etc. spins. If their intrinsic magnetic moment is a 1/2 integer multiple of h bar, then it turns out that you cannot have any two particles that are indistinguishable. Now this confused me when I was in college. if I have two different atoms, I can distinguish this electron belongs to this atom, this electron belongs to this atom. In that case, the electrons can have the same quantum numbers because they're distinguishable from each other. But if I have two electrons in the same atom, they're indistinguishable. There's no way for me to tell them apart. And then you can't have two electrons with the same quantum numbers. They can't be in the same quantum state. So that Pauli exclusion principle is just a general fermion property. Protons and neutrons are also fermions. They're also 1/2 integer spins. You probably, unless you've done NMR, never talked about the spin of a proton or the spin of a neutron. But they have spin. And so this Pauli exclusion principle also applies to protons and neutrons. Of course, we don't use the same quantum numbers for protons and neutrons that we use for electrons. Now, because electrons have only two possible spins, spin up or spin down, what does that mean? It's talking about the orientation. All electrons have a spin quantum number of s equals 1/2. Now, this is a lowercase s. And so the spin angular momentum, so this here is spin angular momentum. That's the uppercase S. Same as what we just did, except for it's the spin number instead of the magnetic quantum number, the orbital magnetic quantum number. And so doing this calculation real quick, 1/2 times 1/2 plus 1, so 3/2. 1/2 times 3/2 is 3/4. And so for all electrons, not 3/4, 3/2. No, that's 3/4. I did it wrong here. 1/2 times 3/2 is indeed 3/4. So it should have been that. Yeah. So that's what I should have had. I can't believe I made that mistake. I probably copied it from a textbook that made the mistake. So they all have that spin angular momentum. We call it spin. They thought that they were actually spinning, but no. Now, just like with the total angular momentum, we had the orientations. So with the spin angular momentum, we're going to have the spin orientations as well. And so then we put in m sub s for our spin magnetic quantum number. And that's going to tell us about the alignment, the orientation of the electron spin. Now, I have a picture here somewhere. Okay. I have a picture somewhere coming up that's going to show the picture like I drew of the circle with the different angular momenta for spin. So now we have a total of 4 quantum numbers. N is the principal. And it can be any integer. And then we had L, which I believe I called it the orbital which is any integer less than n. And then we have m sub L, it's our magnetic. Any integer between plus L and minus L, including 0. And then we had m sub S, which is, and I've always just called it the spin. You notice up here it said spin magnetic because it's the magnetic quantum number associated with spin. And that's either minus 1/2 or 1/2 because spin is always 1/2. So going from the same rules. So those are the quantum numbers you need to describe the state of an atom. And according to the Pauli exclusion principle, no two atoms can have the same one. Second and last clicker question. How many quantum numbers are required to specify the state of a hydrogen atom? Notice I said not the electron, but the state. the hydrogen atom. Now we know it's going down to MacArthur or Darrow. Okay, I'm gonna go on in 5 seconds.
It logged me out.
It logged you out.
Yeah, I'm almost back.
Okay.
Okay, it's not letting me log in.
It's not letting you in. Remind me after class, okay? Okay, so we have 1, 0, 1, 6, 10, 0, 0. So, hey, look at that. We have, depending on what Caitlin would have said, we could have had a majority with one answer. But I'm really surprised, since I've said it like many times, we don't have unanimity. Caitlin. Yeah, you, Caitlin.
I said 4.
And why?
Because you have like isn't there 4, you did say 4, but there's the N, and then the plus or minus 1/2.
Yep, what I just wrote right there. So we have those 4 quantum numbers. You need all of those to describe the state. So here's a summary that's exactly what I just wrote, except for it comes from a textbook. And so it put orbital angular momentum for the quantum number, right? I said orbital magnetic for the one I called magnetic, and then spin magnetic for the one I called spin. What's important is what they're telling you. The L is telling you the total orbital angular momentum. The M sub L is the orientation of that rotational orbital angular momentum. M sub S is telling you the orientation of the spin of the electron. And N is telling you the total energy fundamentally. So how do we label these things? Here's the way that we label a state. We put the principal quantum number out front. We say that labels the shell. So the first row of the periodic table corresponds to putting electrons in the first shell. So hydrogen, you're putting an electron in N equals 1. And then, of course, if N is equal to 1, what does L have to be? 0. So in the hydrogen, you're putting in N equals 1, L equals 0, which demands that M sub L is also 0. But then you have 2 possible M sub S states. You can have M sub S is up or down, plus 1/2 or minus 1/2. So the hydrogen just has 1 electron. It could be either way. You go to helium, you put in the second electron, and one's going to be up, one's going to be down. And then you filled the entire L equals 0. For L equals 0, we never say L equals 0. Instead, we say it's an S orbital. So S orbital means L equals 0. If L equals 1, then we call it a P, and so on. So the S, P, D, F, G, H, that is just telling us what the L quantum number is. Now, if we go down to lithium, lithium has 3 protons in the nucleus, hence we're going to have 3 electrons. The first electron is going to go to the lowest energy state possible. Which number tells us about the energy state primarily? N. So it's going to go to the lowest value possible for N, which is 1. And so the first one's going to be N equals 1, which demands L equals 0. And then it's M sub L is likewise 0, and it's going to be either spin up or spin down. The second electron will go to the other L equals 0 state in 1, so it'll be down, and we'll have a pair. But then the third one, there's no more n equals 1 states available, so it has to go to the next higher state. So it's going to go to n equals 2. Within n equals 2, what values can L have? 0 or 1. Well, which do you suppose is lower energy, 0 or 1? 0. And so it's going to go into the L equals 0, so it's going to be a 2s for that third electron. And the fourth electron, if you go to beryllium, it's going to be another 2s. Once you've filled up the 1s and 2s, you get to boron. You're in n equals 2, you can have L equals 1, the p's. And so for boron, you're going to put in 1 electron into the 2p. For carbon, you're going to put a second electron into the 2p. Now comes another rule. What direction is the first electron going into boron's, 2p? Okay, we just say up. Does it matter? Only if you put it in a magnetic field does it matter. But we say up because that's going to be the lower energy state. What about the second electron that's going into 2p? You have a lower energy if they're aligned together. And so the next one's also going to be up. So you're going to have, when you're filling for the carbon, if you show the 2p's, you have M sub L of -1, 0, and 1. The first one, it doesn't matter. Well, actually it does. The first one's going to go like this. That's the boron one. The carbon one's going to go like this. And if you were to go to nitrogen, what would the third one do? It'd be in the plus one, also pointing up. And then if you put in a fourth one, then it's got to go the opposite direction. And you're increasing the energy as you do that. So you fill out, and when you get to neon, finally, you have a total of 6 electrons in the 2p, all of them paired up. And then you have to go down to the next row. Sodium and magnesium, of course, you're going to put 3s in sodium, 3s2. The 2 means 2 electrons in the s for magnesium. And then the next electron, you would think, would go into, it goes sp, so it should go to p, right? And it does. The next electron is going into the 3p. So aluminum through argon is filling up the 3p's. And then once you're done with the p's, that is the L equals 1s. Since N equals 3, L can go up to 2. And so after you've finished out with argon, you would expect the next electron, you go to potassium, would be in the 3d. But it's not, because 4s is lower energy than 3d. So it goes into the 4s. So the first 2 electrons for potassium and calcium are 4s's, and then going from scandium over to zinc, you're putting in the 3d's. Now we get to the final interesting thing about this. The final interesting thing is, if you look at the electron structure, does that table tell you things like, 2p3 stuff on it? Doesn't have it? Oftentimes, they will actually give you the configurations, and they will assume full shells, like argon, and then it'll show you just what's going on after that. And what is really interesting is, of course, how many electrons can you fit in an S? You can fit 2 because there's only 1 L, and there's 1 M sub L, but 2 M sub S's. In a D, you can have 3 M sub L's, each one with 2 M sub S's, so you can have 6. That was a P. I said D, I said P. In a D, you have 5 M sub L's, each one with 2, so you can put 10. If you get to the ones out here where you're getting to the 5th one, so 1, 2, 3, 4. Okay, here, go back to chromium. Chromium should have 4 electrons in the 3D. It doesn't. It takes an electron that would have been in the 4s and brings it to the 3d, so you have 5 electrons, and then you have all the electrons in the 4s and all the electrons in the 3d are all aligned together. And it actually gives you a lower energy state. So you have some filling anomalies here because, once again, of the alignment rules. That everything is about lowest possible energy state. And so you might have learned somewhere along the way Hund's rule about how the electrons are filling. And that rule is simply based on, and yes, you might pronounce it Hunt instead of Hund. It's simply based on the lowest potential energy possible as you fill.